Hello! So today's topic is the current mirror. What are the typical applications? How did it work in detail? And how can we build up a current mirror with discrete components? See you after the intro. Today I will explain the basic function of a current mirror, its typical applications, the requirements for the current mirror transistors, the theory of operation in detail, a calculation to prove the theory of operation, then how to build a current mirror with amplification, how to build a current mirror for copying current, and finally build up a discrete current mirror and do some measurements on it. And at the end of the video I have a special info for my English speaking followers. The basic function of a current mirror is that a current I1, which is flowing through the transistor T1, is generating an identical current I2, which is flowing through the transistor T2. Typical applications for current mirrors are current control current sources, current amplification, and copying current to different circuit parts. The requirements for a current mirror are identical transistors, especially the base emitter diode characteristic, the gain, and very important, the temperature must be the same. These requirements are fulfilled in an integrated circuit. Due to the fact that the two transistors on an integrated circuit have experienced during production exactly the same processing parameters, the transistor parameters are nearly identical. And due to the tiny distance between the two transistors and the good thermal conducting of the semiconductor, the temperature is also nearly the same. Therefore, current mirrors are usually implemented in analog integrated circuits. Theory of operation. The current I1 flows mainly as the current IC1 through the transistor T1, and a small part of it flows as the current IB to the base of transistor T1 and T2. Due to the fact that the base emitter diode of transistor T1 and the base emitter diode of transistor D2 should have per definition the same characteristic, the current IB is equally distributed to the current IB1 and IB2. Also per definition, the amplification of transistor T1 and the amplification of transistor T2 should be the same. So the current of IC1 and IC2 must be the same. If the amplification of transistor T1 and transistor T2 is high enough, the current IB is negligible compared to the current IC1. So we have here IC1 is equal to I1 and IC2 is equal to I2. So we can say I1 is equal to I2. Now let's do the calculation. I1 is IC1 plus IB. IB is IB1 plus IB2. Due to the fact that IB1 and IB2 are equal, we can say IB1 is equal to IB2 is equal to 0.5 IB. We rearrange the formula and get IB is 2 times IB1. Now we can replace IB with this term here and get I1 is IC1 plus 2 times IB1. IC1 is this current, and this current is IB1 times amplification factor beta from transistor 1. So we get I1 is beta times IB1 plus 2 times IB1. Now we can rearrange the formula to I1 is beta plus 2 times IB1. We rearrange the formula to IB1 is I1 divided by beta plus 2. Now we go to I2. Here we have I2. I2 is the base current IB2 times the amplification factor beta. So I2 is beta times IB2, and due to the fact that IB1 and IB2 are equal, we can write I2 is beta times IB1. We rearrange the formula to IB1 and get IB1 is I2 divided by beta. Now we replace this IB1 by this term and get I2 divided by beta is I1 divided by beta plus 2. We rearrange it to I2 and get I2 is beta divided by beta plus 2 times I1. And now we see when beta is a large value, this term becomes 1, and we can say when beta is a very large value, then I2 is equal I1. To build a current mirror with an amplification factor, we simply need to increase the number of output transistors. Due to, per definition, all these transistors have the same characteristics, the current which is flowing through T0 will also flow through T1 and through T2 and through T3 and through Tn. So if we have 4 output transistors, then we will have 4 times this current, and the current I2 is then 4 times the current I0. Or in general speaking, I2 is n times I0. Sometimes it is necessary to have in different circuit parts the same current. Then we can use the current mirror for copying the current. As we already told, the current I0 through the transistor T0 is equal to the current through transistor T1 is equal to the current through transistor T2, and so on. So we can copy the current I0 to the circuit parts connected to I1, connected to I2, connected to I3, and connected to IN. To build up a current mirror with discrete components in the basic form like this will not work. The reason is that even with selected transistors, the characteristic of the base emitter diode and the gain do not match exactly due to manufacturing tolerances. And even more important, due to the physical separation, the temperature of the semiconductor chips do not match. The base emitter characteristic and the gain change significantly with the temperature. Let us have a deeper look inside this circuit. We have here the 12 volt supply on the top, and the current I1 is flowing through the 10 kilo ohm potentiometer, through the 1 kilo ohm resistor, and through the transistor T1. The voltage at the collector is about 0.7 volt because the collector is connected to the base, and the base emitter diode has a voltage drop of 0.7 volt. On the other side we have T2, and in the beginning the current IC2 is equal to IC1. But due to the low internal resistance of the ampere meter, the voltage drop on T2 is nearly 12 volt. So we have here equal currents, but here a low voltage drop and here a high voltage drop. Current times voltage is power, so we have here low power and here high power, so this transistor will warm up faster than this transistor. With the higher temperature of T2, the base emitter voltage of T2 will become smaller than the base emitter voltage of T1. And additionally, the amplification factor of T2 will become higher than the amplification factor of T1. So the base current IB will be not any longer distributed equally. Due to the lower voltage drop, more of the current will flow to IB2 than to IB1. So the current which is amplified in transistor 2 will become higher, and due to the higher amplification factor it will become higher too. So IC2 is now bigger than IC1. With the bigger current and the high voltage drop, the transistor T2 becomes even more hot. The voltage drop will go down on the base emitter voltage, and even more of current will flow to T2 and less current through T1. And this will lead to a higher warm-up of the transistor T2. We will get a runaway effect, and it could be that if it is not limited by any other thing, like in this circuit, transistor T2 can die. Here our measurement setup. With the ampere meter 1, we measure the current I1, which is the control current. With the ampere meter 2, we measure the current I2, which is the resulting current, and with the voltmeter, we measure the supply voltage. Via the red and blue lines, the power supply is connected to this circuit. From the positive supply line, the current flows through the potentiometer through the 1 kilo ohm resistor via the red line to the ampere meter 1, where we measure the control current, and it goes back via the black line to the collector of the transistor T1. Via this small bridge, the current also is connected to the base of the transistor T1, and the emitter of the transistor T1 is connected via this line to ground. From the positive supply line via the red line, the current flow to the ampere meter 2, which measures the current I2, which is the resulting current. And the current flows back via the blue line to the circuit to the collector of transistor T2. Via this black bridge, the base of T2 is also connected to current I1, and via this bridge the emitter is connected to ground. Measurement 1. The output current is in the beginning 4.74 mA and is increasing. I cool down the transistor T2, which is already hot, with my fingers, and we see that the current goes down. As soon as I remove my fingers from the transistor begins to warm up again and the current increases. To compensate largely the difference in the transistor parameters, especially the one which are caused by the temperature difference, we have to introduce these emitter resistors. When we design the circuit in such a way that for the interesting current range the voltage drop of the emitter resistors is at least 1 volt, and the base emitter voltage difference of T1 and T2 caused by manufacturing difference and especially the temperature difference is not exceeding 20 millivolt, then we will have, for example, on one side 1 volt and on the other side 1.02 volt, which will cause an error of maximum 2%. And the higher the voltage drop across the emitter resistors is, the more precise the discrete current mirror works. We have the same measurement setup as before, but the two direct links from emitter to ground on each of the transistor is replaced by a 200 ohm resistor on each side. Measurement 2. At the beginning, the current error is only 0.03 mA. During the complete warm-up phase, the current changes only a little and remains within the 2% range. I will now reduce the current I1 to 1 mA, which will lead to a voltage drop of only 200 mV at the emitter resistors. And this low voltage drop will cause a bigger error in the discrete current mirror. With the two emitter resistors, we can also adjust the current ratio of I2 to I1. If we, for example, use here 200 ohm resistor and here a 100 ohm resistor, and due to the design of the current mirror, here the voltage is nearly the same of this one, so the current on the output side is twice of the current of the input side. But make the ratio of RE1 and RE2 not too big, because then you move to different operation areas of T2 and T1, and this could lead to a nonlinear behavior of your current mirror. Here the 200 ohm emitter resistor of T2 is replaced by a 100 ohm resistor. Measurement 3. We have now a ratio of I1 to I2 of 2. And I start with 5 mA and reduce the current down to 1 mA. For optimizing the discrete current mirror, the following topics should be considered. Use selected transistors with good matching parameters. Choose transistors with a high gain. Design the circuit with a high voltage drop on the emitter resistors. And most important, ensure a good thermal coupling of the mirror transistors. When using power transistors for the mirror transistors T1 and T2, the gain is often low. To improve the circuit, it is a good idea to add this transistor, which amplifies the base current. Then the current here is also very small and can be neglected. And now an info for my English-speaking followers. About 99% of the views of my videos are from Germany, Austria and Switzerland. And the number of views of the English version is also significantly lower than that of the German version. So I came to the decision to only offer the German version and to use the free time for more new videos. I hope this is also good for you. I hope that the English-speaking followers will stay with me and use the Google subtitle translation function. Thank you very much. That's all for today. If you like my video, give me a thumbs up and subscribe my channel. And to be informed about new videos, activate the bell. See you in the next video. Bye bye.